Hi guys, it's Mrs. Allison. Today we are going to continue the idea of finding volume of solids of revolution, and this time we're going to look at the washer method. And as the name implies, if you guys know what a washer looks like, there's a hole in the middle. We're missing part of it because sometimes our cross sections are circles, they're circular. We have that rotation, so they're circular, but they have that missing part in them. In this case, our cross section is what we call a washer. So a washer is a object that has an outer circle and an inner circle. So if we were to look at this geometrically, and I wanted to find the area of just the shaded region, what I would do is I would find the area first of the large outside circle, and that area would be pi capital R squared. And then I would take away from it the area of the smaller inside circle, so pi little r squared. So that would be the area of the face of this particular shape. Okay, well, let's visualize what these look like. And I'm actually going to do just the second one on here. You can go ahead and click on either of them if you would like to play with them. We are going to look at that second option from GeoGebra, and I wanted to look at this and show you that we have an outside function of 1/3 x plus 2 and an inside function of y equals 6, and we're rotating it about the line y equals 8. So if you look at this diagram here on the bottom left, you can see in the two-dimension plane, if we were just looking at the xy plane, that's what it would look like. Okay, to look at its rotation, what the image is on the right now is a completely rotated shape. And what I want to show you what it looks like is if we drag this slider just a little bit, it's a little bit choppy today, but if we drag this slider, you can start to see those two shapes take form. And what you can see happening is it's creating that shape where if we were to take a slice of this right now, what we would see is we would see that washer shape. Okay, so using that idea, that washer shape, and that second or the first GeoGebra that's listed actually has, you can see the washers and you can kind of play with the size of the washers just a little bit. So that's fun too. It just wasn't loading as well. We want to talk about the volume of the solid of revolution here. And when this region is revolved around a line, but it's not one of the boundaries, its volume is formed with the sum of all the washers, right? Most of them or some of them will have holes in them, and that's why we have to use the washer method here. So if there's any place where there is a distance between the two functions and what we're rotating by, we will need to use the washer method, okay? And the way that we do that is we use this formula, the volume equals pi, the integral from a to b, so the a to b region, of the outer radius squared minus the inner radius squared, dx or dy, depending on if we are using, oops, I left off a parenthesis, if we're using with respect to x or with respect to y. Is it rotating around something related to x or something related to y? What I hope you see is it's really not that much different than what we did yesterday with the discs. So let's look at some examples. Okay, so we're going to start by just setting up the integrals for these and look at how we can find the volumes of the solid formed by revolving the region bound by y equals negative x squared plus x and y equals 0. Now I want you to look at this first example. Is there going to be a hole, a gap in any way between the shape I'm rotating and the line I'm rotating about? No, there's not. If you picture rotating this, right? If we picture rotating this around, I'm going to end up with a shape like this, where what's rotating around is just going to be the disk method. So this is actually the disk method, and this is how we would know to use that, is because there is no gap between what I'm rotating and what I'm rotating about. So my radius here, remember the radius is the top minus the bottom, and the top here is the function. So it'd be negative x squared plus x minus the bottom, which was just the axis, y equals 0. So my radius is negative x squared plus x. So the integral I would set up here would be pi from 0 to 1, my bounds of integration, that's where it starts and ends on the x-axis, of the radius squared, pi r squared, because that's the area of a cylinder, area of a circle, multiplied by dx, that height of that cylinder, that infinitesimally small height. Okay, well that was kind of just to see if you could look at that problem and recognize that it's something you've already done before. So now let's change it just a little bit. Let's say I have that same line, y equals negative x squared plus x, that same curve. But now what I want to do is I want to rotate it about the line y equals negative 1. Y equals negative 1. Okay, so if we want to rotate it around y equals negative 1, what you're going to see here is that this distance from the point of rotation up to the top of the circle would need to be the same down here. So we might have a line that looks something like this down here. We'll pretend those are evenly spaced. And so we have this shape that looks like this. So this is covered in red. My red highlighter is real fat, apparently. Okay. And so if you can picture this, if we were to draw a disc is not going to be able to connect both of these. So I'm going to have to draw a washer where I would have the big outside part, and then I would have an inside part that was missing part of that washer. Okay, so you can see that that washer here, that outside part, connects the two tops. Now what I'm concerned with, and I'm going to erase the washer for just a second, what I'm concerned with, let's just do that, is the radius. So my first step is always to consider what my radii are going to be. So in this particular problem, I need to consider both my outside radius and my inside radius. And the outside radius is, how we find this is we draw it from the axis to the function. Okay, not the rotated function, to the original function. And it's going to be the top minus the bottom. Okay, top minus the bottom. I'm going to erase that R for a second. Okay, so my capital R in this case is going to be the function top would be negative x squared plus x minus the bottom. Well, the bottom was negative 1. So this outside radius here, right, is my radius from the point of rotation up to the function. Okay, so we do top minus bottom. So my outside radius is negative x squared plus x plus 1. Now my inside radius, my little radius, has to do the same thing. We draw it from the axis to the function. Well, the function here happens to be 0. So the top minus the bottom would be 0 minus negative 1. So my radius here is 1. Now when I set up my integral is going to be set up pi times the integral from a to b of r squared, capital R squared, minus little r squared, in this case dx. It's dx because it's rotating around the x, it's not the x-axis, it's around the line y equals negative 1, which would make the cross-section perpendicular to the x-axis, which is why we will have choose dx. So substituting in here, we're going to get the integral from 0 to 1. I chose these bounds because my original function has a domain from 0 to 1. The point, the shaded region that I am finding the volume of goes from 0 to 1. And r squared, capital R squared, will be negative x squared plus x plus 1 squared minus little r, which is 1 squared, and this is with respect to x. So this would be the volume of this shape rotated around. All right, I want you to take a second, hit pause, and try part C. Try rotating it around about y equals 2. All right, hopefully you had a chance to look at rotating this about y equals 2. Now, unfortunately, I didn't leave myself much room to draw this, or at least draw it to scale. If I were to draw this to scale, this might look like this, and I'm going to draw it over here for just a second, just so you can see it. So we had this piece that is right here. This is actually my axis, and this is in green, right? So this is this piece. And what would happen is, about the line y equals 2, I would evenly space out my other part of my function, so I might not have it quite so big. Might have it look something like this, right? And so rotating this shape around, we can see that this is very clearly going to be the washer method, because when I rotate this around, there's going to be a big gap between the two, and you can see the outer and the inner radiuses here, or radii. Okay, so the first thing we want to identify on these is the outside radius, the capital R. The outside radius, you'll notice, remember, we have to start with the original function, and we're drawing it from the axis of rotation to the function. So the axis of rotation, the axis of rotation to the function takes me down here. And so my axis of rotation is 2. The first function I'm dealing with is that the outside part of that function is the line y equals 0. So my outside radius is going to be 2 minus 0, or 2. My inner radius, however, the littler radius, is going to be from the top function, which is 2, that axis of rotation. And I'm going to subtract the actual function. So I'm going to subtract negative x squared plus x. So I get 2 plus x squared minus x for that radius. Now remember, when I set this up, the volume for this particular one is going to be pi times the integral from, well, the bounds of integration have not changed on this one. So from 0 to 1 of my outside radius squared minus my inside radius squared. Oops, that's not a plus, that's a minus. And it's with respect to x, so dx. Okay, how'd you do? All right, let's try some other ones. Hopefully you had a chance to try these, you try your hand at these, and the difference really is that we're revolving a region bound by 2 distinct functions. Okay, 2 distinct functions. So we have y equals x squared and y equals x plus 2, and we're going to rotate that region about whatever line is suggests. So this first one is about the x-axis. And what you can probably picture, or hopefully you can picture, because, or maybe even draw it, something like this. Okay, so if we draw this here, and I'll just color it in red because I don't have an orange. If we draw this here, picture this being rotated around. And we can clearly see that we're going to need the washer method here, because there is definitely going to be a gap in between the function. The gap's going to continue to get bigger and bigger. Okay, so if we were over here, my washer, oops, didn't draw that very straight. My washer would have a much bigger gap in between, right? So we need an outside radius and an inside radius. So we are going to go from top to bottom. So my outside radius here, the top function is very clearly the x plus 2 minus the bottom, or the axis of rotation in this case, which would be minus 0. And my inside radius, well, let's simplify that. That'd be x plus 2. So my inside radius, my little radius, is going to be the top function that I'm rotating, which would be x squared. Sorry, the inside function that I'm rotating would be x squared. And it's going to the axis of rotation, which is 0. So x squared minus 0. We get x squared. So when I go to set this up, we know that I would have the volume of the integral from r squared, so x plus 2 squared, minus little r squared minus x squared. And we know this is going to be with respect to dx. But what about those bounds? What are my bounds going to be? How am I going to figure that out? Well, in order to find my bounds, in order to find the bounds, I'm going to need to find their intersection points. Okay? And if we know the bounds are the intersection point, maybe I can see that intersection point from the graphs alone. And maybe I can't. Maybe I need to set the two functions equal to be able to find their bounds of integration. Sometimes the bounds of integration have to be found using a graphing calculator. It all depends on the problem. So here we get x squared minus x minus 2 equals 0. Factoring, we get x minus 2x plus 1 equals 0. So I know my bounds of integration are 2 and negative 1. So when I fill those in for my bounds of integration, I now have a complete volume formula for this particular function. Okay, hit pause and try the last one in case you haven't already done so. All right, hopefully you had a chance to try the last one, and hopefully you can visualize what's happening here. Okay, so we have this line y equals 4, which we're going to be rotating around, right? And so hopefully you can picture what this might look like. We're going to have a parabola up here, something like this, and then a shape that looks like, we'll pretend this is exactly what it looks like, something like this, okay? And this is what the shape is that we're going to be rotating. Now keep in mind, when I think about my washers here, I didn't draw it very closely to scale, but I tried. When we think about the washers here, we can think about the big outside function and the inside function very similarly to how we did the last one. So let's start with capital R. The outside radius. Well, keep in mind the outside radius, we need to subtract bottom from top, so top minus bottom. And the top of this radius actually is the line of rotation. So it'd be 4. And 4 minus x squared would be the radius going from the line of rotation to the outside function. And then little r then would be 4 minus, that other function was x plus 2. So little r would be 4 minus x minus 2, so 2 minus x. And when we go to set up this formula, we would get the volume equals pi, the integral from negative 1 to 2. The bounds haven't changed. Then we're going to do capital R squared, so 4 minus x squared squared, minus my r, my little r, and my little r is 2 minus x squared, and this is with respect to x, so dx. How'd you do? All right, well, that's the washer method. So as you can see, very, very similar to the disk method. Really, it's just based on what you're given, what the graph looks like as it's rotating. Is there a hole in it or is there not a hole in it? And actually, one of the homework problems I gave you last night on your disk homework, part 2, was actually a washer with respect to y. So maybe go back and try that problem now. You do have an assignment tonight in WebAssign. And we will see you soon. Have a good day.